Hey everyone. In this video, I'm going to talk about inference with normally distributed data. So up to this point, we talked about computing confidence interval based on large sample properties. So based on kind of invoking the central limit theorem and knowing that as soon as the central limit theorem applies, the distribution of a sum of random variables follows a normal distribution, we were able to basically quantify the uncertainty around a large set of estimators, irrespective of the distribution of the underlying random variables, because we knew that the central limit theorem applies with a sufficiently large sample size. Okay, and this is really useful because, as we said, it works with a large variety of distributions as long as we have large enough samples, essentially, right? But in some cases, we might not have large enough samples, but we still might want to characterize the uncertainty around our estimators based on very small or not invoking these asymptotic properties and large sample properties, right? And so one case where we can do this without invoking the central limit theorem is if our data are normally distributed, okay? And so if we have normally distributed data, so if our our outcome variable that we're interested in, is IID, so is independent and identically distributed, follows a normal distribution with some mean mu and some variance sigma square, then we know that x bar, so again, this is the distribution of x bars across repeated samples, follows a normal distribution with mean mu and variance sigma squared divided by n without the central limit theorem. And this is a key kind of insight, that if the random variables themselves are normally distributed, then we know that the x bars follow a normal distribution. So the sampling distribution follows a normal distribution without the central limit theorem. So without we don't need a large sample if the underlying random variable is actually normally distributed. Okay, and that can be a huge help if we're working with smaller samples, right? Again, the standard error is basically the same. The standard error is sigma hat divided by the square root of n. That's basically the same formula for the standard error than we had in the previous case. We also have that without the central limit theorem, we can compute what is called the t statistic, which is the deviation between x bars, that's our sample estimate, and the true population average mu divided by our standard error, follows exactly a t distribution with n minus 1 degrees of freedom. So t n minus 1 is the student t distribution with n minus 1 degrees of freedom. So in this case, where we have normally distributed data, we can use the t distribution rather than the standard normal distribution, which we did previously with the in the context of the central limit theorem, to obtain the critical value for our exact confidence intervals. Okay, and one important thing to note about the t distribution is that as n increases, so as our sample size increases, the t distribution ultimately approaches a standard normal or approaches a normal distribution. Okay, lastly, the confidence interval based on the t distribution for smaller n's is wider than the confidence interval based on the normal distribution. So essentially, the t distribution has wider tails than the normal distribution. Okay. So in that sense, the t distribution, and we're going to talk about the t-test in more detail in the next week. While the t-test basically, or like this t distribution basically makes the assumption that your underlying data, your underlying random variable, is in fact normally distributed. We can even use it for other cases where the underlying data is not normally distributed, if we're willing to kind of invoke the central limit theorem, because then ultimately what the t statistic will give us is always a more conservative inference. The confidence interval will always be wider than the normal distribution, or the confidence interval based on the normal distribution, since the t distribution has wider tails, right? So even if the data are not normally distributed, we can use the t distribution, because ultimately it will be more conservative, because if anything, we'll have wider confidence intervals than we would have if we just relied on the normal distribution. Okay, so how does this t distribution look like? Here's a quick summary of different t distributions with different degrees of freedom that we computed here, and just plotted in a simple graph. And as a comparison, the black line here is a standard normal distribution that we've seen before, centered at 0, of course, standard deviation of 1. And we can see the basic t distribution is also centered at 0, looks very similar to the normal distribution, but has heavier tails. And as the degrees of freedom are lower, or with lower degrees of freedom, these tails ultimately become heavier. So there's basically more uncertainty with fewer degrees of freedom. Okay. So we're going to talk more about the t distribution and t tests in the upcoming week. But just briefly, I want to show you a quick summary, going again back to the minimum wage study, but now computing the confidence intervals based on the student's t distribution rather than using the central limit theorem and the normal distribution. And again, we don't have to assume that these employment rates are necessarily normally distributed if we kind of invoke the central limit theorem and basically look at this as a more conservative way of computing the confidence intervals, okay, because of the heavier tails of the t distribution, okay. Just very quickly, we can look at two different, we're going to just look at the cross-section comparison and the pre-post comparison. Again, this is the average treatment effect of the cross-section comparison. And we're going to use the t-test command here to just directly get the averages in both groups. We'll look more at the t-test command in a second. There are a couple of parts, or a couple of objects that the t-test command returns. The estimate object itself just gives you the averages in both groups, and you can also look at the confidence interval directly, which is basically a shortcut to directly compute the confidence intervals for this difference using the t distribution rather than the normal distribution, with of course appropriate degrees of freedom given those sample sizes. Okay. And you can compare these confidence intervals now to the confidence intervals that we computed previously, which are these ones here are of course a little bit wider than the ones that we computed by hand previously. Okay, we can do the same thing for the before and after comparison. We just plug in those two values before and after in our t-test command. We can look at the estimates as the average values in both groups, and compute the confidence interval, or directly extract the confidence interval from this t-test output as well. And again, these confidence intervals here are wider than the ones that we computed by hand, because the t distribution has heavier tails and is therefore more conservative in that sense. Okay, so this is kind of the special case of inference based on normally distributed data. Again, we can use that more generally because ultimately it's more conservative than only assuming a normal distribution by virtue of the central limit theorem. There's an additional kind of strategy for inference in the book that you should definitely check out as well, which is a randomization-based inference, which is based on not on the argument of sampling or on normally distributed data, but rather based on kind of variations in the treatment assignments kind of looking at how different observations were assigned to treatment on control group, and basically randomizing the data with assumed kind of different treatment regimes where people were assigned in different treatment and control groups rather than the groups that we're actually in order to kind of, under the assumption that there was no treatment effect whatsoever, what would the distribution of possible kind of by chance treatment effects look like for different treatment assignments, and then use that as kind of the equivalent of the sampling distribution, and do hypothesis testing and so on based on that. Make sure to check that out as well. We might talk about it a little bit more in the next week as well. But this is all we have for now, focused on central limit theorem and normally distributed data. All right, I'm looking forward to our discussion in the next Q&A session.